Good afternoon. Welcome to ENST noon seminar. Today's seminar is both our noon seminar and also exit seminar of Taylor Roswall, who's giving this seminar as part of her exit seminar. She has her defense scheduled for later this evening. I'm going to keep it short because I know Taylor has many slides. We also have a faculty meeting at 1, so we need to wrap it up quickly. Taylor grew up in East Tennessee, and then she decided to just go as far as she could in West Coast, where she received a bachelor's degree in biology from UCLA. I know she told me the story, but I keep forgetting. Somehow she ended up in Southern Maryland, where she worked with an American chestnut land trust for about 2 years. And then somehow she found us in ENST and began her grad studies in fall of 2019. So this is her 4th semester in ENST. I have so many good things to say for Taylor. She has just made my job advising her really easy and fun. She has a lot of energy, which is both good and old, which is, I think it's good. And I think Taylor has done a really fantastic job with her sort of thesis research. You have to realize someone coming with biology degree and trying to dig into soil and water science is not easy. But I have been very pleased with her sort of deep understanding of soil science, and especially as connected with phosphorus. So pandemic presented some challenges. She couldn't get to lab earlier, so we had to be creative with her one chapter that she's going to talk about today. But Taylor, the floor is yours, and it has been a pleasure knowing you, and I'm excited for you to give this seminar and graduate, hopefully, pretty soon.
Yeah, definitely. Thank you so much, Dr. Tor. And I'm going to go ahead and share my screen. Let's see here. Share screen. Okay, let me know if you guys can see this okay. Are you able to see this?
Yes.
Okay, great. Well, thank you so much, Dr. Tor, for that introduction. Today I am going to be presenting on my thesis, which is titled Quantification of Water Extractable Phosphorus Pool in Soils and Manure to Accurately Predict Phosphorus Loss. And before I begin, I'd just like to thank Emily, Anya, Stanley, Charles, Izzy's, Dr. Duncan, Dr. Hill, and all of the participating farmers who helped me with this research and made it possible. All right, so today I'm going to give you guys a quick introduction and some motivation for the research, and then I'll dive into chapter 1 and chapter 2 of my thesis. All right, so what is phosphorus? Well, essentially, it's just an element on our periodic table. It's an important nutrient for human, animal, and plant growth, and it's one of the 3 main nutrients that's common in fertilizer, along with nitrogen and potassium. And as of recently, it's gained a lot of infamy because it's directly contributing to a decrease in water quality. So to really understand why it's having some negative impacts on our water, we must first look to how it's cycled in the United States. And prior to World War II, what we were seeing was a tight coupling of nutrients in a complete phosphorus cycle. This was really due because, agriculture had these dual crop livestock operations. Operations is really a stretch. They were more so, small scale farms that were meant to feed families or like local communities, but they rarely went beyond state borders. And to do, we also had smaller crop yields than what we see today. So it's between, 20 and 30 bushels of corn per acre. And this is mainly because this was before the fertilizer boom. So, farmers had to be really conscious about what they were putting into the soil and what they were taking out of the soil. So overall, we just had, stable levels of phosphorus in our soil. If we fast forward to today, we have had the boom of commercial fertilizer industry. And what we're noticing is that we have a broken phosphorus cycle. So we're really seeing unilateral movement from those mines in areas like Florida that are then shipped off and used in the Midwest, where our primary corn and grain production occurs. This is then shipped off, overseas or to other areas where we have intensive livestock operations, such as on Maryland's eastern shore. And instead of that manure being brought back to the area where it was used to grow crops, it really stays local. And this has to do with, how heavy and expensive manure is to transport. And so usually the best and cheapest option is just to apply it to those nearby fields. So over many years of this, we've been building up our phosphorus levels in the soils, and essentially we refer to these soils as legacy phosphorus soils. This just means that they have so much phosphorus that they're now essentially leaking into our water sources and causing eutrophication. And not only are they causing eutrophication, which is bad, but our global phosphorus reserves are actually limited. They're supposed to peak by the year 2030 and could be depleted in as little as 20 years beyond that. So if we're to see, a sustainable future of agriculture having the same amount of production that we see today, we're going to really need to think, rethink how phosphorus is cycled, both on a local and on a global scale. All right, so what's so bad about this manure application? Well, historically, manure was applied based on nitrogen requirements, and in crops, crops need about 8 times more nitrogen than they do phosphorus. But in manure, what we're seeing is nitrogen to phosphorus ratios more on the scale of about 2 to 1. So this means that when farmers apply manure to their fields based on the nitrogen requirements of crops, they're actually adding up more than 4 times the amount of phosphorus than crops can use. So essentially, we know that we have way more phosphorus going into the soil than the plants can use. So how are we dealing with this? Well, in Maryland, we've already developed numerous tools to help us out, such as a nutrient management plan, which essentially just has farmers test their soils for nutrient levels. They're given back results that kind of recommend the correct use of fertilizer. We've also switched from a nitrogen-based application of manure to a phosphorus-based application of manure. In addition, we have these BMPs, or best management practices, which just overall aims to reduce soil erosion. And while these are beneficial for the environment, it's important to think about what this means for our farmers. So essentially, if a farmer gets his soil tested and it comes back that his phosphorus levels are off the chart, he's going to be told he can no longer apply that manure. This means he's going to spend money in order to dispose of it or to transfer it, to a different site. And say while his phosphorus levels are high, his nitrogen levels may be deficient. So this means he's going to have to spend more money to go out there and buy fertilizers. So as you can imagine, this has led to a lot of tension and turmoil between our farmers and our scientific community and the government. And ultimately, if it's not recycled properly, it's just a waste of that critical phosphorus reserve. All right, so let's take a step back and just see in general, where is phosphorus coming into the Chesapeake Bay? Well, it's coming from 3 main sources. We have our agriculture, our urban and suburban landscapes, and then our sewage treatment plants. And in 2010, the EPA recognized, the negative impacts of phosphorus on our water quality, and they set a goal for the Chesapeake Bay watershed. That goal was to reduce our phosphorus loading by 4 million pounds per year before the year 2025. And as you can see, agriculture has about half of this loading. So what better way than to target this non-point source? So how are we doing in terms of meeting this goal? Well, recent research showed that in some areas of the Chesapeake Bay watershed, we are seeing that reduction in phosphorus loadings. But in other areas, such as on the eastern shore of Maryland, we're still seeing a continued increase. And these researchers attributed this to that manure management I was discussing, as well as the presence of legacy phosphorus soils. All right, so why are we continuing to see this phosphorus increase, despite those nutrient management plans, our switch to a phosphorus-based application of manure, and all those best management practices. Well, we know that these legacy soils have extremely large reservoirs of phosphorus because of this long-term manure application. We also know that phosphorus removal by crops is not high. So even if farmers, quit applying phosphorus to their fields, the rate at which crops are going to mine this phosphorus is definitely not fast enough to meet those EPA goals. But what we do know is that we first need to really understand what's going on in these legacy soils, and we need to be able to quantify the different pools of phosphorus. And to do so, obviously, we need accurate methods. And this is extremely important for that most soluble phosphorus pool. And this soluble pool is also known as the water extractable phosphorus pool. Like its name suggests, it's just the phosphorus that can be extracted with water. It's a simple laboratory extraction that really simulates how much phosphorus will be lost from the soil during a rain event. It's comprised of both dissolved inorganic and organic phosphorus species. It's highly labile, meaning it can easily sorb and desorb from the soil, which means it's directly available to both plants and algae. This also means that it's easily lost to waterways. So, because of this property, it's commonly been used to assess the risk of phosphorus loss from fields. And this research stems back to the early 90s, where they found that the higher the soil's water extractable phosphorus levels, the more dissolved reactive phosphorus that would be lost into the waterways. All right, so this brings us to chapter 1, which is titled Hotspots of Legacy Phosphorus in Agricultural Landscapes, Revisiting the Water Extractable Phosphorus Pool in Soils. So the overall goal was to gain further insights into the water extractable phosphorus pool of legacy soils. And from here on out, I'm just going to refer to it as WEP. Okay, so our hypothesis was that these current WEP methods that were established before we recognize legacy soils, they're not extracting the entirety of the pool because of equilibrium constraints between the low soil to water ratios. Our specific questions was, are current methods for extracting WEP working in these soils? If they aren't, what's a better method to quantify the WEP pool? And finally, are we able to fully quantify and fully exhaust the WEP pool during lab extractions? So the first thing we needed to do then was we needed to go out and find us some of these legacy soils. And legacy phosphorus soils, the definition is really broad, but what we decided to do was we decided to define it as soils that had a MELIC 3 phosphorus value above 500 milligrams per kilogram, because this level is used as an environmental threshold in our region. And just as a reference, this MELIC 3 extraction is essentially a measure of how much phosphorus is available to plants during a growing season. And anywhere between 50 and 100 milligrams is optimum for crop growth. All right, so these legacy soils in Maryland constitute about 18,000 acres or 1.6% of our total agricultural area. And 86% of this acreage is concentrated on the lower eastern shore. So this is where we decided to head to, and we selected 8 sites, 1 in Caroline, 2 in Dorchester, and 5 in Somerset counties, all with values above 500. So here are those MELIC 3 values. Again, we have them ranging from about 534 to 1,127 milligrams per kilogram. And again, to put this in perspective, this is between 5 and 20 times more phosphorus than what the crops can utilize. All right, so we went out into these sites and we selected a uniform area. Within that area, we defined a 4 by 7 meter plot where we took 10 random samples and then combined them into one field composite sample. And just some information about these soils. They're pretty normal in terms of what we expect to find on the Eastern Shore in Maryland. They had normal pH ranging from about 6 to 7. organic matter anywhere from 0.5% to 3%, and then soil texture from loamy sand to loam. Obviously, what was unique about these soils was their phosphorus levels, which range from about 700 to 2,200 milligrams per kilogram. All right, so we took our samples back to the lab and we decided to split the extractions and analyses into two parts. So part one was aimed to answer the question, do we need a new method for extracting WEP? And to do this, we took 4 ratios of soil to water, which essentially just means we took 1 part soil to either 10, 20, 50, or 100 parts water. And just for reference, that 1 to 10 and 1 to 20 ratio, those are the common methods used in the Mid-Atlantic region. So part 2 was aimed to answer the question, how large is this WEP pool, and will these soils ever stop losing phosphorus? To do this, we began with an initial 1 to 100 extraction ratio, and then sequentially extracted the same soil 8 times. This resulted in, a final ratio equivalent of about 1 to 800. So once we had our mixtures, they were shaken for an hour, centrifuged, and filtered. And then analysis occurred 2 different ways. We performed colorimetry to determine, our main inorganic WEP species, and then spectroscopy to determine our total WEP. And then organic was taken as the difference between the 2. All right, so what did we find? So part 1, here we have results from the first set of extractions. We have our ratios across the x-axis and then our amount of WEP across the y. We also have our inorganic species in blue, our organic in green, and then our total in red. So first, let's look at the inorganic species, and what we're seeing, oh, sorry, I forgot to mention, just as a reminder, the 1 to 10 and 1 to 20, those are the conventional ratios. All right, so what we're seeing as we increase our extraction ratios is that we're seeing significantly more inorganic WEP. This increased from 23.7 at the 1 to 10 to 58.5 at the 1 to 100. And this is due because of an equilibrium-induced barrier. So what do I mean by this? Well, in soils, during this extraction, essentially WEP release is controlled by an equilibrium between what's in the water and what's on the soil. So in theory, as we add more water to our soil, we will be able to extract more phosphorus, assuming that there's phosphorus there to begin with. So here I'm showing 2 ratios. We have that 1 to 20 in the bottom and that 1 to 100 on the top. And if we focus in on the bottom, what we're seeing is that solution or that water phase is fully saturated with phosphorus, even though there's plenty more phosphorus on the soil to be extracted. It's just it can't hold anymore. So that's why that arrow is pointing more heavily towards the soil. However, if we go into the 1 to 100 ratio, we've now added more water. We see that there's less phosphorus concentrated on the soil because that phosphorus was able to desorb into the water. In this case, we're seeing more true equilibrium status is reached. So while these 1 to 10 and 1 to 20 ratios are doing a good job in these lower phosphorus soils, what this is showing is that it's just not enough water to allow the full pool to be released in these high phosphorus soils. All right, so what about the organic pool? And here we're focusing in on those green box plots. And what we see was that there was an initial increase at the 1 to 20 ratio, which was followed by subsequent decreases. And this is not what we expected, or at least I didn't expect this. I expected the organic to follow trend with the inorganic species. And so we looked into the individual sites, and what we found was actually, they all began to decline at different ratios, and the ratio in which this decline occurred was correlated with the soil's total phosphorus. So here I have an example of 3 sites along with their total phosphorus values. In site 2, this was our highest total phosphorus, and we really saw organic WEP increase throughout the ratios up until that 1 to 100. In site 5, this was more on our medium range. We saw an initial increase at the 1 to 20, and then finally a decrease at the 1 to 50. And then finally in site 8, this was on the lower scale. And we really saw the highest concentration of organic WEP during that initial 1 to 10, with decreases followed. So what we hypothesize this is due is because we're increasing those ratios, we're allowing for more WEP to desorb from the solid phase, and this is allowing organic WEP to then preferentially bind to those soil binding sites over our inorganic species. All right. So finally, let's look at our total pool, which again is in our pink box plots. And this time I've added a new graph at the top, which just shows the composition of total WEP in its inorganic species in blue and its organic in green. All right, so we notice that total WEP is following the same trend as inorganic. It's increasing across the extraction ratios from about 30 milligrams to 63. If we look at the top of the graph, what we're noticing is that inorganic WEP is comprising about 78% of the total at the 1 to 10, and then this is increasing to about 93% at the 1 to 100. This is important because, oftentimes in research, we're seeing either colorimetry or spectroscopy to measure our WEP pools, but really never both at the same time. And honestly, colorimetry is used more often. So what this means is that, if you're extracting these soils using colorimetry at these more conventional methods, you're going to be disregarding a significant portion of the WEP pool. All right, now I want to try to put what we've been talking about in context with other phosphorus pools in soil. And here is a simple diagram I found that essentially describes the pools of phosphorus in terms of their availability or how fixed they are in the soil. So pool 1, that's our WEP pool that we've been talking about. And as we go along to pool 4, essentially the phosphorus is becoming more fixed and not available. So if we take that pool 1 and pool 2, this combined, this is what's readily available to our plants, and this is called the melic 3 pool. So in terms of melic 3, the WEP that we were extracting was between 4 and 8%. If we look at the total WEP pool, which is all 4 of these pools, what we're seeing is that WEP was 2.3% at the 1 to 10 ratio. And just for reference, in non-high phosphorus soils, what we see are percentages very far below 0. So essentially this tells us that, our pools that we're seeing here is just very, very large. And this transitions well because, part 2, we were determined to find out just how large this WEP pool was, and will these soils ever stop losing phosphorus? So just to remind you, this is where we did those sequential extractions, which gave us an equivalent ending ratio of about 1 to 800. So here are these results. We have our sequential extraction number across the x-axis, along with the concentration of WEP along the y, again split into inorganic and organic parts. I've also added the site's total phosphorus levels just for reference. And the first thing to note is that, no, we were not able to fully exhaust the WEP pool during these extractions. In fact, a non-zero equilibrium was reached in every soil pretty much after that initial 1 to 100 ratio. And here's the values of this equilibrium concentration, which was little different in each soil and correlated well with its total levels. And really, I want to point out this dotted line across the bottom of the graph, which represents the EPA's total phosphorus limit for surface waters, which is 0.03 milligrams per liter. So essentially what this means is that even if we exhaust these soils of their WEP species to the point that we were able to during these extractions, they're still going to be releasing concerning amounts of phosphorus into our waters. And just to put this in some sort of perspective, on how much water we actually used. I'm going to give you a very, very rough calculation, which is by no means accurate, but it gives you some sort of an idea. So we have about 40 inches of rain in Maryland a year. This equates to about a 1:20 ratio in our top 5 centimeters of soil. So essentially it would take 40 years of rainfall to get to the amount of water that we added during these sequential extractions. And really what this means is that, even if we keep targeting this soluble pool, either, it's lost in runoff or it's being mined by our crops, it's not enough to bring these levels to meet our environmental goals. So essentially we need to explore the use of chemical amendments that aim to transform these more labile phosphorus pool into those fixed or recalcitrant pools that I was just discussing. All right, so some take-home messages from chapter 1. First and foremost, we recommend using a 1:100 ratio when determining the wet pool. As we saw, this would eliminate any discrepancies between research that uses colorimetry or spectroscopy. It should also be an easy transition for most labs, as it's already the ratio that's used with other high phosphorus sources such as manure and biosolids. And finally, what we saw was this wet pool is just so huge in these soils, and we really need more innovative techniques in order to mitigate the losses. And if you're interested in anything else, I'm happy to say that this paper was just published last week. So be sure to check it out if you have any more questions or interest. All right. So for chapter 2, unfortunately, as Dr. Tor said, I wasn't able to get out in the field and perform my own research, but there was an available data set from 2007 that hadn't been published or really analyzed, and I was able to make it fit in nicely with the overall topic of my thesis. So chapter 2 is titled Dissolved Phosphorus Loss in Runoff from Soils Amended with Poultry Litter and Products, the Effects of Laboratory and Simulated Litter to Water Extraction Ratios. So just to remind you what we know in terms of manure. So we know that Maryland has a huge amount of chickens. We also know that Maryland has a bunch of legacy soils, as this graph above shows, and this is mainly because we have historically applied this chicken manure in excess. We now know, because phosphorus is negatively impacting our waterways, that many of these farmers are no longer able to apply manure to their fields. But seeing how critical it is of a phosphorus reserve, where should this excess manure go? A thing to consider is that manure has a high concentration of water. This makes it very heavy and therefore very expensive to transport. We also know that to help mitigate this phosphorus loss, we have implemented manure management strategies which advocate for a total phosphorus-based application of manure versus a nitrogen-based application. But even with this, over a period of time, we're still going to see excess phosphorus levels in soils. So is there an even better alternative to this total phosphorus-based application? Can manure be applied on a wet basis? And also, are we able to turn this manure into a product that is easy to transport and could be marketable to other landscapes such as, lawns and turf? So the objectives of chapter 2 was to investigate the dissolved phosphorus runoff losses when poultry litter and products were applied on a wet basis. The specific questions was, how does a wet-based application correlate with dissolved phosphorus loss? Does processing poultry litter through granulation and heating result in a product that could be used on other landscapes? And specifically with these poultry litter products, we wanted to know, what's the effect on the dissolved phosphorus losses and what's their effect on soil phosphorus levels? So this was all done, as I said, in 2007 using conducted rainfall simulations and packed soil boxes. And research in the past has shown that these packed soil boxes are actually a good representation of what occurs in the field, at least in terms of dissolved phosphorus loss. All right, so why was a wet-based application chosen, and which poultry litter products and why? And before I begin, I just I've been using manure, now I'm saying poultry litter. Essentially, poultry litter is just chicken manure, but it has some of this other stuff like urine and bedding material from the poultry houses. So just think chicken manure when I say poultry litter, but I will be referring to it as poultry litter from here on out. All right, so why WEP? Well, we know that WEP is large in poultry litter. It's about 20% of the total phosphorus, whereas if you remember from chapter 1, we were only seeing about 1% in soils. We also know that WEP is highly correlated with dissolved reactive phosphorus in runoff. So can it serve as a better prediction tool? And really we wanted to see, can litter be added to these high phosphorus soils even on, low amounts, and will it create significant runoff? In terms of the poultry litter and products, raw litter was chosen because this is what represents our field applications. The raw litter was granulated and then urea was added, and this aimed to balance those nitrogen to phosphorus ratios so that we could potentially create a marketable product for urban landscapes. And then finally, the litter was heated, and the goal of this was just to reduce the water content, eliminate the odor and microbes, which makes it safer and cheaper to transport. All right, so here are some of the characteristics of the poultry litter products. And again, with the granulated litter, the main goal was to increase that nitrogen to phosphorus ratio. And then with the heated, the main goal was to get rid of all of the water content. So if we look at the bottom of the table, here's where we have our extracted WEP amounts at these varying ratios. And the first thing to notice is that in the raw litter, we're seeing kind of what we saw in chapter 1. So we're seeing this equilibrium restriction to the entire WEP release at those narrower, like 1:10 ratios. However, we're not seeing this in the granulated and heated litters. And ultimately, what the processing of these litters did was it just essentially created a fertilizer. So it took all of that phosphorus and it made it fully soluble once it was to come in contact with any amount of water. And this was mainly due to the dissociation of those magnesium and calcium phosphorus compounds. All right, so now we know a little bit about our poultry products. Let's look into how the experiments were conducted. So here's a diagram of the packed soil boxes and then the rainfall simulation, where you can see that there was constant water applied across the entirety of the soil box. So a representative Arkansas soil was used to pack the soil boxes, 12 kilograms of soil at a bulk density of about 1.2. Then the poultry litter and products were applied on top of the cheesecloth at a rate of 3 kilograms of WEP per hectare, based on those extracted amounts at the 1:10, 1:100, and 1:200 ratio. So overall, this resulted in 24 treatments. We had raw and granulated litter applied at all 3 ratios, heated litter applied at 1:100, and then a controlled treatment where no litter was added. This was performed in triplicate as to account for any random variables. All right, so this is what those packed soil boxes actually looked like. And as I said, the rainfall simulations were conducted back in 2007 over a 3-week period on days 1, 7, and 21 after the litter was applied. And this was done according to the National Phosphorus Project Protocol, which was simply developed to streamline these types of experiments in order to gain further understanding across different areas and across different research. So the boxes were rained on at an intensity of 7 centimeters per hour until runoff occurred. This is equivalent to a storm in Arkansas with about a 5 to 10 year return period. It really only took 10 minutes to generate runoff, and the resulting rainfall to runoff ratio was about 0.83. So in all cases, the runoff volumes were recorded, and then a 1 liter composite sample was analyzed for dissolved reactive phosphorus and total dissolved phosphorus, where dissolved unreactive phosphorus, or DUP, was just the difference between the two. All right, so let's look into some of our results. Here I have the cumulative losses across the 3 simulations, and we have the type of manure across the x-axis along with the extraction ratio used for application. So we're seeing our raw litter in pink, our granulated in green, and then our heated in blue. Also, there's the control added on the left-hand side just for reference. And we have our dissolved reactive phosphorus, or DRP, in the bottom, and then DUP, or dissolved unreactive phosphorus, in the top. So what we're seeing is that this total loss ranged from about 0.89 to 5 kilograms per hectare. We're seeing, it's looking higher in the first 2 applications of raw litter, but essentially not very different among the final 4 treatments, which was the raw litter 1 to 200, all of the granulated litters, and then the heated litter. What we're also seeing is that the DRP composition was about 68% of TDP, but really it was higher in the granulated litter. It was about 80% of TDP, and this is problematic because that DRP pool, as its name suggests, is the most reactive and is the most available for those toxic and proliferate algal blooms. So if you can remember, the litters were added based on 3 kilograms of wet per hectare. So it seems like it could be correlated in the final 4, but what's going on with those first 2 applications of raw litter? And is this telling us that DRP is actually not correlated? Well, I'm about to change your mind on how much WEP was actually added to the soil boxes. So here we have the simple water extractions in terms of the litter sources. We have our raw in pink, our granulated in green, and heated in blue. And what we're seeing is that as we increase that extraction ratio, we're seeing more raw litter released. And this is due to those equilibrium barriers that I discussed in chapter 1. But really that's not occurring for our granulated and heated products. And like I said, those are more acting like fertilizer, where they have full solubility no matter how much water is released into the soil. So in 2004, it was pretty well established that a ratio of 1 to 250 was a good representation of the total wet pool in manures. So essentially, we recalculated the amounts of WEP added based on this new extraction ratio and found that really it was added anywhere between 3 and 17 kilograms of WEP per hectare. All right, so now let's relook at those same results and see if they make a little more sense. So now we're seeing, yes, it looks like the amount of WEP added is correlated with both the DRP, or dissolved reactive loss, as well as the DUP loss, which means, yes, total dissolved phosphorus loss is correlated with WEP. What we're also seeing is that the losses here range between 24 and 43% of what was added. This means that we are going to see significant runoff of dissolved phosphorus, even when we're applying manure at super low application rates. So unfortunately, this means that it's probably not going to be beneficial or able to be applied to those high phosphorus soils. All right, so initially I told you that we applied the litter on top of a cheesecloth, but I didn't tell you why. And essentially this cheesecloth just physically separated the soil from the litter during the simulations, so that once the simulations were complete, the soil could be tested to see how the litter affected its WEP content and its MELIC3 content. So let's look into the WEP content first. I've underlined the control treatment just because this is what we use to compare all of the other treatments against. And what we're seeing is that really only the raw litter 1 to 10 and 1 to 100 application increase soil wet. And this is hypothesized to be because in these litters, we're applying significant amounts of organic matter that when they start to decompose, they will release organic acids such as citrate and malate that will outcompete this labile phosphorus. It will outcompete them to get to those binding sites, which essentially just means that they're going to be left in the wet pool. If we look at all of the other treatments, we're seeing that none of them really affected the soil wet levels. So this could mean a couple of things. It could mean that, adding litter in general based on 3 kilograms of wet per hectare will not significantly affect soil wet levels. It could also mean that, these heated and granulated litters don't affect soil wet levels at all. It's just we would need to investigate them at higher application rates. All right, so how about the melic-3 content? How did these poultry litter products affect it? Well, what we see is that the melic-3 content increased with the addition of all litters. So I've underlined that control treatment again. So really the addition of litters increased melic-3 from about 7 to between 10.5 to 42.6 milligrams per kilogram. This was not correlated with the amount of WEP added, and actually it depended on the litter type. So if you look in that third column where it says melic-3P increase, essentially this is a calculation that's done to give us the expected increase in a soil's melic-3 level per kilogram of total phosphorus added. So what we're seeing here is that it was consistent across the litter type. If you look at the raw litter, we're seeing about 2 times more than what we're noticing with the heated and granulated litter. And another study looked into this, similar increase, and what they found was that a monopotassium phosphate fertilizer also increased the soil's melic-3 between 0.3 and 0.4, which really just drives home the point that these granulated and heated litter products are acting like fertilizer. This other study did not look at poultry litter specifically, but they did look at dairy manure. And I just thought it would be interesting to add this point. So dairy manure increases it anywhere from about 0.1 to 0.2. So if you can see our poultry litter increasing it to 0.7, now maybe you can understand why we have these insanely high melic-3 values near poultry operations on the Eastern Shore. Okay, so in summary from chapter 2, we once again learned that the extraction ratio methodology matters. We need to be able to calculate exactly how much WEP is going in there. We also learned that adding litter to soil, even at these low extraction rates, can generate significant runoff and therefore is not a viable option for continued manure application in high phosphorus soils. We saw that adding litter less than a rate of 3 kilograms per hectare does not increase the soil's WEP content, but it does increase the soil's melic-3 content, and this increase is consistent across litter types. So just to put the 2 sections together, this means that the granulated and heated litter products, they're going to provide the same amount of WEP as raw litter. It's actually going to be more soluble, meaning it's going to be, more available to plants. It's not going to have significantly more runoff, and it's definitely not going to increase the soil's melic-3 content. This means that, we can turn poultry litter into products that could be used for other settings. So that's all I have today. I know it was a lot of phosphorus and chemistry, but I hope that you could take at least something away from it. And thank you so much for taking your time and listening.
All righty. Well, thanks very much, Taylor. Very interesting presentation. And we'll try to take some questions in the chat box. There's a few coming in already, so I'll pass those along.
Okay.
So here's a question from Dave Tilley. So Dr. Tilley says, in one of your introductory charts, you showed the phosphorus contribution to the bay. He thinks it like 46% ag and 25% municipal, 25% urban. She's wondering which years is this based on, and was this estimate made before or after the WSSC changed over to the chloramine water treatment process, which forced them to add phosphate to the water supply to reduce the lead dissolution in the old distribution lines?
Does he know so the graph was from 2010. So if he knows when that switch occurred, I'm not sure if that was post 2010 or not, but the graph I was showing was just from 2010 to set the stage for the US EPA goal.
Okay. Dave, you want to comment or?
Yeah, I think they changed the system back in 2003 is my recollection. So then your data should be after that.
Okay.
Thanks.
Yeah.
Okay, so Dietrich is asking, he says, you mentioned that the phosphorus might be immobilized using a chemical approach. What strategies do farmers have available to them that could affect this equilibrium and immobilize some of the phosphorus in the soils?
Right. So I didn't look more into this, but essentially what strategy is the cheapest to farmers right now is just to quit applying manure to their fields. And essentially what needs to be done is, this isn't going to meet our goals. So we need to get some sort of chemical transformation that's going to tie up those phosphorus binding sites, which in these soils, it was mainly due to the presence of iron and aluminum. So something that can get in these soils and bind those sites up to where just the overall amount of available sites to have soluble phosphorus in will be decreased. So I'm not sure if, I know we have some NRCS people on here. I'm sure that they could give you more information on some of the chemical amendments that are being, experimented with, I guess. But in terms of it being like cheap and farmers willing to use it, I'm not sure how far that's making progress right now.
Let me throw out a potentially unusual sort of amendment. And this comes from some work that Bruce James and I did 25 years ago related to phosphorus absorption in some created wetland sites. But we worked with an engineer who suggested we use steel wool as an amendment. And mixing the steel wool into these, at this time they were sort of wetland sites, but it oxidized to form a very poorly crystalline ferrihydrite, which had an immense phosphorus absorption potential, way higher than sort of the normal iron oxides that you see in soil. So
right.
I don't know what the cost ratio sort of would be on steel, steel wool, but there may be some sort of innovative things like that.
That would be interesting. Like, I'm assuming that it could be done when they, cultivate their fields, like every so often. They could just turn it into the top 5 centimeters.
Yeah, you mix it in, and then it takes usually, some probably weeks or months. It's pretty fine, so there's lots of surface area to sort of completely oxidize to form the ferrihydrite. But in a relatively short time, within a season, you'd think it would be essentially all converted and available for absorption. So. But again, I don't know what the cost of that is relative to sort of other sorts of products. So Dr. Rupert asks, can the phosphorus concentration at iteration 8 of the sequential extraction be predicted by the results of iteration 1? You only have 4 data points, but do your other 4 data points fit into a neat function?
Sorry, is your question just like, can the amount extracted by number 8 be predicted?
Yeah, with only, if you just do your initial extraction of 1 to 100, can you extrapolate out to what you get after 8?
Right. So didn't have time to put all of my data in this presentation, but essentially what you find is that in that final ratio, it's anywhere between 200 to 500% of that initial extraction. So in other words, no, I mean, while the trend is the same, like the exact, like fitting a direct equation to that data was not, it was not, was not done, and nor could it have been, because we did have like a 200% gap between the final extracted amounts. And that's mostly due just because you saw that site 2 had 2,200 milligrams of total phosphorus compared to one of our other sites that only had about 800. So essentially it was very dependent on the total amounts.
Okay. And Dr. Wild says, what about adding aluminum iron compounds to the poultry house litter to reduce the ammonia and bind the phosphorus? He says farmers are doing this because it increases chicken growth due to a lowering of the ammonia gas within the chicken house, which I guess is toxic to the chickens.
Yeah, I mean, I definitely think that there's a lot of stuff going on in terms of manure. I think as like the main, again, this unfortunately wasn't my exact research with the manure portion, but I believe the main goal was just to turn it into a product that isn't going to be smelly and that's very cheap to transport, so that we could get a profit from it. So I'm not sure if if we add aluminum to the poultry house itself, if then the farmers will be able to use it on their landscapes more. But unfortunately what we saw was that even adding little bits of manure, we're still seeing almost 50% of what's added in runoff, which means that it's just not going to be an option to these high phosphorus farm fields.
Great. Yeah, maybe they could add steel wool in the manure within the chicken house or something and catch it early. So, well, fantastic presentation, Taylor. Thanks so much.
Thank you.
And lots of good questions, and best of luck in the rest of your defense later this afternoon. I'm sure it'll go well.
Oh, thank you so much.
And let me just point out to everyone, I just added again into the chat box the link to complete the evaluation form for Taylor. So if you'd please do that, that would be great.